For months, astronomers have watched the interstellar visitor 3I Atlas glide inward through the solar system. Telescopes around the world and above it have tracked its every shift in brightness, every subtle change in its coma, every flicker of activity. Yet nothing in that slow accumulation of data prepared researchers for what the Hubble Space Telescope recorded at the end of November. The new imagery did not merely refine our understanding of the object, it revealed something far larger, far stranger, and far more structured than anyone had anticipated. Avi Loeb, examining the data, emphasized that the November 30 observation unveiled a feature so pronounced and so unusual that it immediately demanded deeper investigation.
Let's just wait a few more weeks, we'll figure it out, and let's hope that there will be no gifts from this object for the holidays on Earth. If it's a natural object, there is nothing to worry about. Don't lose any sleep for now until we figure out, that it might be technological. In that case, I would start worrying, yes.
The discovery marked a turning point in the study of this object, raising the stakes in a way no one expected. This is only the third confirmed interstellar object humanity has ever observed. That status alone imbues every detail with significance. Interstellar visitors are not bound by the same history or formation conditions as the comets and asteroids we know. They are emissaries from distant star systems, shaped by alien environments and physical processes we have not yet encountered. That makes 3I Atlas more than an astronomical curiosity. It is a fragment of another world entering our own. Each new observation could complicate or overturn what scientists think they understand about the materials drifting between stars. And as the days tick down toward late December, its activity appears to be increasing rather than stabilizing. Something is unfolding inside its coma, and the sense of urgency has grown with every new frame captured by Hubble. The November 30 Hubble dataset arrived with extraordinary clarity. Using its sharpest mode, the telescope resolved the comet's inner region at 0.04 arcseconds, one of the finest views yet obtained of any interstellar object. But the clarity of the raw image was only the beginning. To probe deeper, astronomers processed the image through layers of enhancement. First, an unsharp mask to emphasize small-scale structure, then a rotational gradient filter, a method based on the Larson-Sekanina algorithm, long used to dissect cometary comae. This filter subtracts the symmetric components of the coma and highlights subtle internal features that would otherwise remain buried under haze. When applied to 3I Atlas, it did something more than sharpen the object. It exposed a hidden architecture. At first glance, before enhancement, the object resembled what astronomers expected, a soft, glowing sphere of dust and gas surrounding an unresolved nucleus. For most comets, especially at this early stage of activity, the coma is simple. A faint tail may emerge behind the object, but the region around the nucleus is dominated by smooth radial outflow. Standard models would predict nothing more remarkable than the earliest hints of dust structure, if anything at all. Even for a visitor from another star, that simplicity was the reasonable expectation. Astronomers anticipated a symmetrical, unbroken coma, perhaps slightly elongated but far from complex.
But that expectation dissolved the moment the rotational gradient version of the November 30 image appeared. The filtered frame unveiled something intricate, extended, and startlingly directional. Suddenly, the inner coma was no longer uniform. It was sculpted. It was active. It was dominated by features that should not have been so large or so clear at this stage in the object's evolution. Loeb highlighted how striking these features were compared to what observers usually see in familiar comets. The enhanced image had revealed not just activity, but structure on a scale that immediately challenged earlier assumptions. Two jets emerged from the data, sharp, well-defined columns of material erupting from opposite sides of the nucleus. In the rotational gradient processed image, these jets appeared as linear, high-contrast features extending outward with a degree of symmetry not typically observed in early-stage comet activity. Their clarity was notable. Rather than fading gradually into the surrounding coma, each jet maintained a consistent brightness profile over its length, implying a steady, continuous flow of material. The symmetry of the pair, nearly 180 degrees apart, suggests that they originate from discrete active regions on the comet's surface, possibly vents or fissures aligned along a rotational axis. This geometry points to focused emission driven by localized heating or by the exposure of volatile rich layers rather than by random or chaotic outgassing. The directional quality of the jets further indicates that the nucleus may be rotating in a way that periodically reorients these active zones toward the Sun, although the precise rotational dynamics remain undetermined. Yet the jets, striking though they were, did not constitute the most prominent or unexpected feature revealed in the November 30 data. The enhanced frame exposed a large-scale, sunward-oriented structure, an anti-tail, extending across more than 60,000 kilometers. The magnitude of this feature is measurable on planetary scales, roughly 10 times Earth's diameter. Its orientation is counterintuitive. In most comets, dust and gas streams outward and away from the Sun due to radiation pressure and solar wind interaction. Anti-tails represent an exception, formed when heavier dust particles released earlier in the orbit remain in the comet's orbital plane and create the appearance of a structure pointing sunward from the observer's perspective. However, the anti-tail in 3I Atlas is unusually long, dense, and sharply defined compared to typical examples documented in solar system comets. In the rotational gradient image, this anti-tail appears as a narrow, luminous band stretching across the field of view, maintaining coherence along its length. Its visibility at this distance and its clear orientation suggest a distinctive distribution of dust particle sizes, likely skewed toward larger grains capable of resisting deflection by solar radiation.
The structure's extent implies that material released earlier in the object's inbound trajectory has accumulated into a pronounced sheet or stream aligned within the orbital plane. Because the anti-tail extends sunward instead of trailing behind the comet, it contradicts initial expectations about how an object freshly exposed to the Sun's heating should behave. Rather than presenting a single, basic tail pointed away from the Sun, 3I Atlas displays a complex configuration that reflects both its physical composition and the dynamical properties of the dust it emits. Taken together, the jets and the anti-tail indicate a multifaceted activity pattern not typically observed in newly detected interstellar objects. Their combined clarity, scale, and organization provide evidence that the surface and internal structure of 3I Atlas may differ significantly from standard cometary models, warranting further analysis as it continues its passage through the inner solar system. This is the kind of discovery that forces scientists to reconsider the fundamentals of what they thought they knew. Anti-tails are real phenomena, but they are rare, and they depend on highly specific viewing geometries. They form when large dust particles, too heavy to be blown away quickly by sunlight, lag behind in the comet's orbital plane and appear, from Earth's perspective, to point toward the Sun. Even when they occur, they are usually delicate, faint, or fleeting. But the anti-tail of 3I Atlas is none of these things. It is enormous, strikingly clear, and already present at this early stage. That alone would have been enough to raise eyebrows. What makes the discovery even more significant is its persistence. This is not the first time the object has displayed a sunward anti-tail. Hubble's July 21 observation showed the same phenomenon, pointed toward the Sun, and already surprisingly pronounced. The November 30 dataset confirms that the anti-tail has not only endured across months, but grown more structured and more extensive than before. The implication is that whatever mechanism forms it is stable and sustained, rather than the result of a short-lived burst of activity. Loeb highlights this continuity, emphasizing it as one of the object's key anomalies. Jets this distinct further complicate the picture. Such features are typical of comets that have undergone years or decades of repeated heating cycles, which gradually open vents in their surfaces. But 3I Atlas is new to our solar system. It has not experienced previous perihelion passages that would shape and sculpt its nucleus. For it to produce such powerful, organized jets on its first recorded encounter with the Sun
suggests either an unusually volatile-rich composition or an active surface geometry unlike anything previously studied. Its behavior is clearly closer to that of an evolved comet, not a pristine interstellar fragment. The immense scale of the antitail and jets surpasses that of many well-observed solar system comets, some of which have been studied for centuries. The structures in 3I Atlas appear not only larger but more coherent. That coherence hints at underlying processes, rotational dynamics, internal heating, surface topography, that are not yet fully understood. It raises questions about the dust size distribution as well. Larger grains can create strong antitails, and their presence may indicate formation conditions unique to the comet's original star system. Loeb's analysis invites this kind of open-minded inquiry, urging scientists to consider possibilities beyond familiar solar system behavior. Speculation must remain grounded, but several hypotheses can be drawn from the evidence. The jets may originate from vents activated by rapid rotation, causing material to be ejected in opposite directions as the nucleus spins. Surface fractures could channel dust into collimated streams, producing the distinct linear form observed in the Hubble images. The antitail, spanning tens of thousands of kilometers, could be composed of relatively massive dust grains that remain close to the orbital plane, forming a stable sunward structure. Alternatively, the object's interstellar composition, rich in CO2 and potentially containing unusual volatiles, may produce outflow characteristics unfamiliar to solar system comets. Yet none of these ideas fully explain all the observations. Each hypothesis accounts for part of the puzzle but leaves gaps when examined against the full structure revealed by Hubble. The symmetry of the jets, the persistence of the antitail from July to November, the remarkable clarity of the features, and the sheer size of the sunward extension, each detail complicates the simple narrative of a comet awakening under sunlight. As Loeb notes, nature often exceeds our expectations. In the case of 3I Atlas, it may be far more imaginative than our models anticipate.
As December 19 approaches, interest intensifies. The object is drawing closer, and its activity appears to be rising. Observers report that the jets are becoming more defined, suggesting increased release of material from the nucleus. The antitail continues to broaden and lengthen, now confirmed to exceed 60,000 kilometers. These changes imply that the object's next phase could reveal even more dramatic structures. Each new dataset arrives with growing anticipation. If Hubble captured this much complexity at one astronomical unit, what might be revealed when the object moves deeper into the inner solar system? The November 30 observation is the beginning of a more detailed and urgent investigation. The massive antitail, the symmetrical jets, the persistent structural anomalies, all of these traits point toward an interstellar traveler behaving in ways that challenge our expectations. As Loeb suggests through his analysis, the discovery underscores the value of maintaining scientific humility. When objects from other star systems enter ours, they carry histories and physical behaviors shaped by environments we have never seen. They are reminders that the universe is larger, stranger, and more inventive than our current frameworks can capture. As 3I Atlas approaches its closest point, scientists may be witnessing one of the most revealing interstellar encounters of the decade. The structural complexity revealed in the November 30 dataset ensures that the next observations will be watched with heightened interest. What began as a faint, distant speck has become a dynamic, evolving object with features that stretch across planetary scales. And with each passing day, the mystery deepens. The story of 3I Atlas is not finished. It is only the beginning.